Okay, so in this first example, we are going to do that first task that I told you I would teach you about, and that is figure out the limiting reactant. So in the scenario, it tells us iron can be produced by reacting iron 3 oxide in the presence of high temperatures with aluminum in the following reaction. This is a super cool reaction, by the way. Google it. It's called thermite. It's ridiculous. Okay, you take iron oxide, which is essentially rust, and react it with aluminum to produce iron and aluminum oxide. So the reaction uses 100 grams of Fe2O3 and 30 grams of Al. Okay, so real quick, I want you to think and ask yourself, what is a limiting reactant? What does that mean? So that means the reactant that's going to be used up completely. Students will often initially think, oh, that's probably just the reactant that there's less of. Now, maybe, right? This can happen, but we can't assume that. Okay, here's why. Grams and moles are different, like we just talked about. They're the quantities, the number of grams, and the number of moles. Okay, if you have 30 grams of aluminum, 30 moles of aluminum, those are totally different amounts. So we can say that 1 mole of Fe2O3 reacts to 2 moles of Al. It's a 1-to-2 ratio. So we want to see if we react all of this, the 100 grams of Fe2O3 and 30 grams of Al, is that going to be a 1-to-2 ratio? Okay, and we'll see if it lines up. So first step is going to be to convert given amounts into moles. We're going to find how many moles of Fe2O3 and Al we have in the reaction. So we'll do the same thing we did back in the first part, in our launch that we did earlier. So, moles of Fe2O3. We have 100 grams of Fe2O3. I want to pause real quick. I want you to pause this, find the molar mass of Fe2O3. Okay, if you do, you'll find that it's 159.69. Grams per mole. So cancel that out. Okay, we'll divide this out. 6,262 moles of Fe2O3. Same thing for Al. 30. The molar mass for this is pretty easy. All you gotta do is find it on the periodic table. So, whoops. So, go to your periodic table app, find aluminum, and find the molar mass of that. You would get 26.98 grams per mole of aluminum, and we'll divide this out. Grams go away. So we got 30 divided by 26.98. We get 1.11. That's moles of aluminum. Cool. Step 1 is done. We have these amounts of moles that we are working with. Okay? So we should be able to compare what we have to what the recipe or the perfect amount is, which is right here. And if we have a perfect efficient reaction, then these amounts should be equal to these amounts in a proportion. So we should be able to say that 0.6262 is proportional to our ratio, our mole ratio from the equation, which is 1-to-2. Okay, that's Fe2O3. This is Al. So 1 Fe2O3 to 2 Al. But let's see if this actually is this equal or is it not equal? Like we might say this is not equal. We'll have to see. So if we look at the math, 0.6262 divided by 1.11, we get 0.56, we divide these numbers. And when we divide 1 and 2, we get 0.5. Okay? We see that actually there's an imbalance here, right? This is not equal. Okay? 0.56 is greater than 0.5. So if something's greater than, then what's responsible for this fraction being greater than this fraction? It's got to be the numerator. Okay? It's got to be this number making this fraction bigger. So we would say, okay, this means that Fe2O3 is in excess. If Fe2O3 is in excess, then that means the other thing has to be limiting, which means Al is limiting. So we would have used up all of the moles of Al, okay, and had a little bit of leftover Fe2O3, okay? We would have needed a little bit less, exactly half of 1.11. Okay, we would have needed 0.555 moles of Fe2O3 to have had an efficient reaction. Okay, we only needed 0.555 moles Fe2O3. Okay, which means we have some leftover. We have exactly 0.0712 with that many moles of Fe2O3 left over. Okay? So this breaks down kind of why this Fe2O3 is in excess.